Right. Welcome everyone to our webinar, STEDYCON and Huygens Super Resolution Scaled Up, which is a joint webinar by SVI and Abberior Instruments. My name is Joachim Fischer. I'm the product manager of the STEDYCON at Abberior Instruments, and triggered by many customer requests, we have added new features to the STEDYCON that now allow for higher throughput imaging and for larger fields of view, and I'm very happy and excited to present these today. While the STEDYCON development is more focused on data acquisition than on data analysis, we found a perfect match in our close collaboration with SVI that delivers state-of-the-art data analysis tools. And as you will see, they do not only have excellent deconvolution, but also perfect tile stitching capabilities. I'm excited that we have these two excellent presenters today. It's Michel Rahm, that did his master's on soft matter physics and joined SVI as a scientific developer 2 years ago. And it's Dr. Janina Hanne. She did her PhD on STED imaging of HIV in Stefan Hell's lab and is now working at Abberior Instruments as a scientific relations manager. The outline of the webinar is printed here. So Janina will start and introduce STED at the STEDYCON, and then she will give a STEDYCON demonstration from her living room. Michel will take over and introduce the Huygens stitching algorithm, and then also give a workflow demonstration of the Huygens stitcher. And in the end, we are of course happy to answer any questions that you pose. So please don't hesitate, ask any questions in the questions tab of this webinar software. They will be answered in the end, and if this is not possible, we will follow up via email and answer your question. That's it from my side. I'm looking forward to the presentations, and I would hand it over to Janina.
Thank you, Joachim, for the kind introduction, and welcome also from my side. So as you probably know, the Nobel Prize in Chemistry 2014 was awarded for the invention of super-resolution microscopy to Stefan Hell, who's here in the center, Eric Betzig, and W.E. Murnau. Stefan Hell is one of the founders actually of our company, so basically we are a spin-off from his group at the Max Planck Institute. Here on this official Nobel Prize poster, and in the center, there's a STED measurement which comes from Abberior Instruments, and we're really proud to actually be on that Nobel Prize poster. In the corner here, STED is already briefly explained. So basically, it works as a confocal microscope. So an excitation laser is scanned over the sample, and in a STED microscopy in addition, we use a second laser, a STED laser beam or so-called quenching laser beam, which has a donut shape and which turns off the fluorophores everywhere except for the exact center of the donut. So photon emission is only possible from the center, which is much smaller than the original confocal excitation laser beam before. And now to show it to you in a bit more detail, here is our STED image. On the right side, you see STED, on the left there's confocal. So this is a whole nucleus, and the nuclear pores were labeled in 2 different colors. And only in confocal you can actually appreciate the beauty of the flower-shaped shapes, which cannot at all be seen in the confocal microscope. But let's have a more detailed look at STED. So in this rough sketch here, the excitation laser travels through the objective lens, excites the fluorophores on the sample, which are then detected again by the objective and focused on the detector. And even with the best optics, one will always see a blurred spot in the focal plane, which has the size of about half the wavelength of light, which is indicated here on the right side. So in STED microscopy now, we use actually an on-off switching of the fluorophores to generate super resolution. So in detail, we excite the fluorophore to the excited state, in which it stays a bit until it usually emits a photon spontaneously. But here now, we use a second laser, the STED laser, to bring back the fluorophores to their ground state. Luckily, the ground state is dark, so we switched off the fluorophore. The mechanism behind off-switching is stimulated emission, so whenever we have the excited state fluorophore with the laser, the fluorophore is simulated to emit a photon and returns to its ground state. And now we just use the donut-shaped laser beam, which uses stimulated emission to turn off all the fluorophores that are not in the center of the donor STED laser, and by this generates super resolution. Now the STED resolution is not only dependent on the wavelengths and the NA of the objective anymore, but in addition also on the dye properties, and especially on how susceptible the dye actually is to the STED laser beam, which is the value IS here, and additionally on the STED laser power I. Since it is a square root dependence, the curve looks like this, with the resolution on the y-axis and the STED laser power on the x-axis. If we turn off the STED laser, we basically get confocal resolution. And if we turn it on with only little power, we already see a huge difference in resolution compared to confocal. And the further we crank up the power, the more resolution we get. And the last 50% of the STED laser actually squeezes out the last couple of nanometers of resolution. So the beauty of the system actually is that we can tune our resolution the way we actually need it. For example, if we want to image structures with a side of around 100 nanometers, we don't need 20 nanometer resolution to visualize it, but maybe 50 is enough. So we can save a lot of laser power and actually imaging time. But let's have a look at how we make best use of the fluorophore photons. So once the fluorophores are in their excited state, they fall back to their ground state within a certain probability after a defined time. A good indicator for the time it takes for a photon to happen is the fluorescence lifetime, which for standard dyes is around 3 nanoseconds. In other words, we basically have around 3 nanoseconds time to de-excite the fluorophores and to collect their photons. And this is most efficiently done with the pulse STED laser. Because here, after the STED laser pulse, all our fluorophores are in their ground state that we don't want to image, so except for the ones which are actually in the center of the donut. So all the fluorophores that we are detecting after the STED laser pulse are the super resolved photons, and we're simply not detecting the ones which were basically confocal before we used the STED laser pulse. This is quite superior to CW STED, because if you had a CW STED laser, a lot of STED laser light was wasted on the sample, since the fluorophores are already back in their ground state and the STED laser only acts on the excited state, so there's just too much light on the sample basically. This can also be seen from the data in this publication. For the same resolution, which is here on the y-axis, roughly 5 times more laser power is needed in the CW STED case, which is indicated here in blue, compared to the pulse STED case, indicated in orange. In this case, even an 80 MHz system was used, so for the 40 MHz repetition rate that we usually use in our STED system, the STED power is even around 10 times lower for the same resolution. So to sum it up, with pulsed lasers, we need less STED laser power, leading to less bleaching and thus less phototoxicity, and at the same time, we get much better and brighter images. At abberior instruments, all our STED lasers are always pulsed, irrespective of the wavelength, because it is the best technology for STED microscope, if we believe. So in total, we offer 3 different types of STED microscopes. Here on the right, you see the STEDYCON, which is a compact STED microscope, which I will focus on during this webinar. On the other side of the spectrum, there's the Expert line, which is a high-end and highly customizable STED system for 2D and 3D STED, with multiple STED laser options and a super powerful software. For example, there's a Python interface which allows you to control all the microscope parameters and even to script your own experiments. And the Expert line allows you to open the box, align the system, and even modify the optics yourself if you want to. And in the center, there's our Facility line, which combines the best of both worlds. So it is basically as easy to use as the STEDYCON, but with almost all the features we can also provide for the Expert line. It comes with an auto alignment feature, so there's no need for manual alignment, and is thus perfect for a multi-user environment such as a facility, for example. With our Facility line, we get STED images with isotropic resolution, as seen here in this render of a Drosophila larvae active zone, at the neuromuscular junction, for example. Yeah, there's just much more detail in this STED image. And brand new, we have our MinFlux microscope, which allows for isotropic imaging with a resolution of around 2 nanometers, or tracking with super high precision at extremely high speed. And on MinFlux, we'll have a separate webinar coming soon, so in roughly 5 weeks, so stay tuned. But now let's focus on the STEDYCON. So the STEDYCON can be attached to every microscope body. So here, for example, it is on an upright size microscope body that has a free camera port and converts your already existing microscopes to confocal and a STED microscope. The STEDYCON consists of 2 parts. The supply unit on the bottom left here, which has all the lasers and detectors already inside, and then this is connected via the black cable in the background to the scanner head. The scanner head contains the scanner, the faceplate, and the pinhole. Additionally, we use a Z piezo, for example here PFOC for Z stacks and volume imaging. And of course, we have a PC that actually controls the STEDYCON. So here is an example image that we acquired with the STEDYCON. This is a brain section, and here the axon initial segments were labeled for spectrum. So those are 2 different neurons, one next to each other, and thus 2 different axon initial segments. In confocal, here we don't see any structure, but if we turn on the STED laser, one really nicely sees the regular pattern of the spectrum. Keep in mind that what you're seeing here is actually raw data. So we didn't do any deconvolution or any other calculations on the images yet, but of course, we could do it if it helped to improve the image quality, for example. And how to do it in the STEDYCON software is quite easy. So we have an integrated interface with Huygens. So you just click on Send to Huygens, and this image will automatically open in the Huygens software with all parameters already in place. And then one can directly start, for example, with express deconvolution or analysis. Michael will show you later how it works during this webinar. The STEDYCON itself has a lot of advantages. So it doesn't only fit on any microscope frame. It doesn't matter if it's inverted or upright, as long as there is a free camera port and a good objective lens. So the STEDYCON is compatible with any microscope manufacturer, be it Zeiss, Nikon, Olympus, or Leica. On inverted microscope, we usually have the scan head attached to the side camera port, as you can see here on this Nikon microscope. But also is the STEDYCON aligned by design, as we call it. So there is no routine alignment necessary of your microscope. So this is because the STED and the excitation laser are all inside of the supply unit. So they travel through the same optical fiber, and after the fiber, they are not separated anymore. So they cannot go physically out of alignment. So basically, the STEDYCON is a turnkey system. You turn it on, and it works as reliable as it did yesterday. Next, the software is super easy to use, so anybody can acquire STED images with only minutes of training. And I'll show you how the software works live in a second. And as shown in this picture, the software can even run on a tablet. Moreover, the STEDYCON is extremely compact, so there's not much space needed in your lab. It will for sure fit in. I'm quite confident about this because I installed it already in the smallest corners. And at the same time, it is quite affordable for a STED and confocal microscope. Additionally, we can upgrade it with the film unit to do lifetime imaging or super resolution lifetime imaging, or separate different dyes by lifetime, for example. And it has super sensitive detectors. In the STEDYCON system, we use APDs, avalanche photodiodes, and if we look at the photon detection efficiencies of the APDs dependent on the wavelengths, we see that the APDs really excel in almost all wavelength regimes compared to any other detectors on the market. Especially in the red and far red range, which is the important range for STED, photon detection efficiencies are up to almost 70%, which is extraordinary. So this is why we use the APDs in all our imaging systems. Inside the STEDYCON head, we have an integrated autofocus module, the so-called STEDYFocus, which holds the focal plane over hours, for example, like if you want to do time-lapse imaging over hours or days, you can be sure that the cover slip always stays at the same distance from the objective lens. And this comes in quite handy when talking about our new features on the next slides. So one of our new features is the option to do multi-position imaging with the STEDYCON. So first, the STEDYCON allows you to actually discover your sample by making a huge tiled over scan of your sample. And then you can go on and just define your experiments, so define different regions of interest, which are not even within one scanning field, but actually at different positions so that the stage needs to be moved. Then you can define if there shall be a Z-stack, if at this particular region of interest, if a STED or a confocal image is required, and at which STED plane you would actually like to image your cell. And then you go and let the microscope do the work for you. So the microscope is imaging while you go for a coffee or let it work overnight or prepare your next sample. And of course, this can be also combined with live cell imaging, as it was done here with 3 different regions of interest, and imaged every 1.5 minutes for more than 400 frames. So in between every time step, the stage actually traveled to the next cell with excellent precision, and as you see, the cell stayed in focus for almost 10 hours by using the autofocus module. Here we use the brand new abberior Live 610 dye, labeling tubulin, which is from our sister company abberior. Additionally to multi-positioning, we also offer different tiling options. So this image, for example, is a cross-section of a lily of the valley root, which we acquired Z-stacks from for 81 tiles. And this huge data set was then stitched with the Huygens software, which also will be shown later by Michael. So far for the introduction. Now let's have a look directly at the STEDYCON.
Alright, so welcome to my living room. Here's the STEDYCON. It sits on an Olympus iX83. It has a motorized stage, a iX3 SSU, and a ZPH stage on top, so we can freely rotate the objectives as we need it, basically. It sits on an Acurion anti-vibration table, which is just on a normal table. And underneath here, below the table, there's the supply box, which has all the lasers and detectors inside. Of course, we stick to the rules and declared our living room here a laser safe area. As you see, we put up some warning signs. So let's have a look at the software. Great, now here we are in front of the STEDYCON software. This is the first window which asked us to define our session, which we'll do now. So we give it a session name and a sample name. In this case we have a cell sample. Everything will be saved later automatically in a folder that has today's date and session name, and the images will be labeled by the sample name. The objective which we have here is a 100x objective with an NA of 1.45. It's an oil objective lens, and it's actually the new X-line objective from Olympus, which works extremely well with our STEDYCON. Next, we choose from a list of dyes here the dyes that we actually have in our sample, and in our case it's the star red, the star orange, and the star green. And by choosing the dye presets, we not only set the excitation lasers and the detectors correctly, but also determine what is actually the expected resolution for each dye, dependent on the STED laser power that we've chosen. And depending on the expected resolution, we set the pixel size later automatically. So this dye presets are actually quite powerful. So now if we set all of this, let's go. and start imaging. So first we'll acquire an overview image continuously, which helps us to fine focus our sample. We can use the mouse wheel for fine focusing, which I'm doing now, and you already see coming the PMP structures into focus. So the star red labels PMP, which is a peroxisomal protein. The star orange labels the nucleus, and in this case here we need a bit more excitation laser power, like this maybe, and the star green labels vimentin. And here is how it looks like in the overlay. Now we zoom into a position of interest that we would like to acquire a STED image from. Let's choose here maybe. It zooms in automatically but still acquires a confocal image, so this gives us the chance to fine focus again in the zoomed in version already. Now we'll activate STED. Also choose here for the second the excitation laser power a bit higher. And now we'll define our resolution, and in this case we'll go for about 60 nanometer resolution, and this sets the STED laser power accordingly for the two different dyes. Dye 3, the star green, is not compatible with the 775 nanometer STED laser because the emission spectrum is too far away, but it actually needs the 595 nanometer STED laser, which we provide in our facility line and expert line. So for dye 3, for the star green, the STED laser or the resolution slider here is grayed out and will always acquire a confocal image. Let's make imaging also a bit faster and go on acquire. It now first acquires a confocal image and second a STED image for the star red and the star orange, and for the star green it will still acquire a confocal image at the same time. And what we'll see here is already the nuclear pores of the star orange look much nicer in the STED image than compared to the confocal image. Let's increase a bit the contrast. And what is always especially great, I think, is the star red channel, where you see the vesicular structures, all the peroxisomes actually, and compared to confocal mode, you don't see any of these structures. It's only a big blob basically, and with STED turned on, suddenly there is a structure actually. So now let me show you our new features. First, we'll turn on the autofocus here, so every time, irrespective of which position we are in the sample, the cover slip actually stays at the same distance from the objective lens. And now we'll do a discover scan. In this case here we'll do a 5x5 discover scan, and just click on discover, and what happens now is that the software requires continuously overview images. Those are all confocal, and moves the stage at the same time. So we see basically if we let the discover scan run over a long time our whole sample, and here you see the single cells popping up inside our sample plane. The autofocus holds the focal plane, so it will not drift out, or if you have sample tilt it will correct for it. And I'm always extremely happy if I see a new cell popping up, like this one, on my sample, and know that my staining has worked, and just looks amazing. So now this was the 5x5 overview scan. Next, on this overview scan, we'll choose our experiment. Basically, we set up our experiment right now, and then let the microscope do the work and the imaging for us. So first, for example, I would like to image this cell here. I add the active region of interest to the list of regions of interest, and move the region of interest now to a different position, for example here. I can really tune the size, rotate even if it fits better to my cell, add also this active fry, and move on to another cell. For example this here. This is quite asymmetric, so there's a lot of peroxisomes on one side, so I try to also catch these and add the active fry. Now I'll activate the region of interest queue, turn off STED for now and just acquire in confocal mode, and acquire my queue. So this acquires a confocal image of the 3 different positions that I've set. Of course, I can also do the same instead and can define my STED experiment like this. For example, here, this region of interest shall be a bit smaller. I update the region here. Region of interest number 2, I don't need, I would like to remove. And region of interest number 1, I also make a bit smaller and rotate it to fit in some of the peroxisomal proteins and a tiny bit of the nucleus. Oops, mistake. Didn't click update but add, but no worries, I'll just remove the first row and then I have the 2 rows defined that I actually planned to image before. Now that's a different region of interest queue, and here I would like to actually acquire a STED image. So I click on acquire queue and we'll first acquire a confocal image of this position and then second a STED image. Of course, I can combine these kind of imaging modalities with Z-stacks, for example, or with time series, or a Z-stack at different regions of interest over time, or whatever you can envision. Of course, you can tell it to the program, you can define it, and then you go for a coffee and let the microscope do all the work for you, basically. Or let it image overnight, or prepare your next experiment, or whatever comes to your mind. But it allows you to have much more free time. You don't need to sit in front of the microscope and actually wait until the sample is imaged, but you can use this time to move on and scale up your experiments. So now let's already have a look at the image gallery. Our images are all automatically saved, and we can have a look at them inside the image gallery. And here are all the images I acquired before. So where's my STED image? Here. Because here now you can click between confocal and STED and have a look how the sample looks like, see the different channels, or a feature that I like most actually is that can export this current image into a PDF. And if it is exported, you get the name of the sample, the name of your experiment, the scale bar, a color bar, all the single channels, additionally an overlay, the same for confocal, and moreover a summary of all the settings that you had. So this is a feature which would have saved me so much time during my PhD, just to show the images to my boss or copy it into my lab book. That's one feature I wish I had. What else can be done here is to do some image analysis. For example, we can send over this image to Huygens. Send to Huygens. And now it automatically opens in the Huygens window. Here it is already actually. What is great about this is that not only the images open automatically, but also the settings are imported automatically. So you can directly now go on and deconvolve your data or do the analysis on your data and so on. So let's go back now to the STEDYCON software. So what else you can do here in terms of image analysis is, for example, you can draw a line profile. So let's draw a line, maybe across this guy here, and fit a gouge into it. Now it tells us what the size of this structure actually is. And this one is 122 nanometers. Let's go on and fit a slightly smaller one, like this. And this now is 63 nanometers. So we're finding structures here which are actually in the size of the resolution, or in the range of the resolution that we're expecting, which tells us that our microscope is actually working really well. And please keep in mind the data we are showing here is all raw data. So we didn't do any deconvolution, we didn't do any analysis or anything to modify the data actually. But this is how you get the data out of the microscope. of course, you can do everything you would like to, like for example, remove some of the background, increase contrast, or go on and deconvolve. But there's no calculation necessary, basically, to directly get good images. So let's go back to our STEDYCON software. Here it finished acquiring the region of interest queue that I set. And you see that the peroxisome structures look incredible. As a next step, I would like to change the sample and actually also change the objective lens. So we'll move on to another sample, which is Telia. It's a 3-year-old stem and a cross-section through it. And we'll have a look at it with the 20x objective lens. Just give me a second until I find the sample. Now in the software you see the stage movement. I'll focus it. You already saw that the objective lens was found now to be 20x. That was all done automatically by the software. So now I also do a confocal overview scan to see if I'm actually close to the focus. Here it is. Such a nice structure. I reduce a bit the excitation laser power. I think the sample is much brighter than the previous one actually. Well, like this here can be a bit increased. And now also here I do a discover scan. To see how my sample actually looks like. With the 20x objective, we have a slightly bigger field of view, so the scan size now is 450 times 400 microns, compared to the 100x objective, where we had 90 times 80 microns. Let me enlarge this here. So nice. Alright, let's stop it for now. And now I'd like to choose a position of interest, like for example this one here, which is slightly bigger than the region of interest that I can maximally scan with the scanner. So what you see automatically, the software detected 4 different tiles, so it calculated that 4 tiles would be the best to image this region of interest here with. And now I move on to the tiling window here. There I can decide what the pattern shall be, like a snake, a grid, or a spiral. I can decide on the overlap in between the tiles, and just then go on to acquire. We don't need that instead. To acquire a tile scan of this Telia image. Actually, we can make it run a bit faster. So if I turn off the automatic line accumulations, the software allows me to image much faster than the minimal pixel size which I have when the automatic line accumulation is turned on. And this way I get my tiled image in no time basically. Of course, this then now can be sent over to Huygens for a stitching with their excellent stitcher module. But until it's ready, I'll just send one image over that we acquired previously, which is this one. It's quite a huge image actually. So here in the preview you see how many tiles we had. So this now I'll send to Huygens and give over to Michael for stitching.
Thank you, Janina, for the insightful demonstration, and hello to the rest of you watching. My name is Michel Ram, and I'm one of the scientific developers here at SVI. Now, I will give you an overview of how we are able to take the images acquired by the abberior STEDYCON microscope into Huygens, and how this ties in to our stitching and deconvolution wizard. So, imaging more tiles allows you to capture larger regions of your object at high detail. Stitching together these tile images is done with dedicated software that merges the tiles into one artifact-free image. And by clicking the Send to Huygens button after the acquisition, you can select the acquired tile series to open directly into the Huygens Stitcher. Here is a selection of the main features of the stitching wizard. We can stitch up to 2D, 3D, but also multi-channel and time series tiled images, and there's essentially no limit to the file size and the number of tiles you can stitch. It performs an optimal automated registration of the tiles in both the XY and Z direction. Even tiles with 0% overlap can be stitched. However, we always recommend to have some overlapped regions between the images. There are tools included for the correction of vignetting artifacts, which I will highlight in a minute. And there's also the option to perform deconvolution. Both the registration and the deconvolution steps greatly benefit from the implemented GPU acceleration in Huygens. And as of the 2004 release, Huygens will recognize all the tile information as included in the new STEDYCON OBF files. This will allow you to perform near automatic stitching, as the tiling layout will be automatically read from the imported OBF files. The next step after loading the images in Huygens is the registration in the wizard. This is done for every tile with respect to its direct neighbors using a cross-correlation approach. This will then lead to an optimal fit of all tiles in 3D space. In the past, we have observed several issues related to stitching. One common issue is the doubling of objects in the overlapping regions of tiles, as you can see in this brain tissue sample. You can probably imagine that any type of analysis and tracing of neurons is severely hampered in such data. In addition, striping or intensity mismatches may appear in the overlapping regions as an artifact. These show up as hard lines on the edge of the tiles. With our automated alignment in the Huygens Stitcher, we aim to prevent these doubling issues. And after the tile registration or alignment is done, the wizard offers the user the possibility to correct the tiles for any vignetting or striping issues. And to also increase the contrast and resolution, you have the ability to perform a deconvolution step for each tile. The vignetting correction is a step that needs to be applied to the single tiles before the actual stitching takes part. It is also preferred to apply the deconvolution on the single tiles and not to the stitched image, so that the computational workload is kept to a minimum. Vignetting is an image artifact caused by uneven illumination of the field of view. It is present in each single tile, however it's not as easily recognizable from the single tile image. By contrast, after stitching, the vignetting becomes clearly visible in the stitched result and appears as an array of square shading over the complete image. The vignetting correction option in the Huygens Stitcher offers in fact two approaches. One is the manual approach, where a dark field and a flat field image need to be recorded in advance to be loaded in the Stitcher. And then there's the automatic setting, which allows the user to select a vignetting model and the profile of its intensity. Each channel can then be selected or deselected for the vignetting correction. This two-channel image on the bottom clearly shows the vignetting artifacts after stitching, whereas the stitched version that was automatically corrected for vignetting in Huygens does not. Next to vignetting, there is the option to deconvolve the tiles before they are actually stitched. This can be done by loading the common Huygens microscopy parameter template and deconvolution template files during one of the stages in the wizard. This allows you to get high resolution detail and high contrast in your stitched image. and it'll allow you to do better analysis in a later stage. Within the stitcher workflow, the vignetting correction and the deconvolution step can be omitted. The next step in the stitching and deconvolution wizard is the actual stitching. The stitching and deconvolution wizard has been optimally designed to make the workflow as easy as possible. Within the wizard's help window, information is provided to guide the users through each step, and the optimal stitcher workflow also ensures a minimum use of computer resources, making the stitching computationally very efficient. Furthermore, the registration of tiles and deconvolution benefit from efficient CPU and GPU acceleration. So, what file size and tile numbers can be loaded in Huygens? Well, Huygens itself poses no absolute limit. The hardware will be rate limiting. This dataset was acquired by imaging 3090 individual tiles with the abberior STEDYCON microscope, and all tiles were stitched using the Huygens stitching wizard, resulting in a field of view of approximately 2 by 2 millimeters with 100 nanometer pixel sampling. Look at the zoomed in region containing a single cell to appreciate the level of detail in this deconvolved dataset. With the new 2004 version of Huygens, the stitcher is further optimized to efficiently handle larger datasets with hundreds or even thousands of tiles, resulting in a super fast and intuitive stitching workflow to generate huge fields of views at high resolution. So next I would like to give you a hands-on demonstration of what it would look like to perform such a stitching routine in Huygens. Alright, so here I have opened Huygens Professional 2004 with an abberior STEDYCON dataset with a lot of tiles. As you can see when scrolling through this menu, this is a tiled dataset with over 1,000 tiles. For the purpose of this webinar, I will only select the first 100 for stitching. This is possible by shift left clicking, and then only the first 100 will be selected. If we then click accept, we can choose to either open them all in the Huygens main window or send them directly to the stitcher with stitch tiles, which we do. Here we can see that the layout is read in from the file, so it's in a spiraling outward pattern. We can verify this by clicking on show tiles. Yes, we want to show the tiles. Let me up the contrast a bit so that it's possible for everyone at home to see it a bit better. Change the gamma first and then up the brightness a bit. See? Right. As you can see, the tiles are loaded in the same order as the acquisition pattern, and we can verify by zooming in that the overlap is indeed set correctly and it's almost perfect. If you were to have a TIFF series over here, then you could set the acquisition pattern from a couple of presets available in the stitcher together with the acquisition overlap, but that is all set correctly from the file, so we can go ahead and click next. In this stage you can remove the tile selection to create one of your own patterns, which tiles you would like to take into account in the final stitched result. However, for the sake of this demo, I'm just going to select them all because we would like to have a square final image, and then click next. This stage allows you to select the vignetting correction options. So there are three options: either not do the correction, or have the automatic vignetting correction on, or the manual one where you would have to load the flat field and dark field images so that each tile is then correctly corrected for the vignetting and shading. For the purpose of this demonstration, I will not do vignetting correction. In this stage we can then select which channels, which colors we would like to take into account when optimizing the layout. So what data needs to be handled when looking at the correct optimal positions for all the tiles in the cross correlation method. Well, in this case I'm just going to leave them all on. That would give you the best results for this data set. And We can even choose if we want to do the alignment in X, Y, and Z, or simply in X and Y, and we can choose that because this is a 2D data set, and that will improve the registration timing a bit. So we can then click Next, and as you can see, each tile is then compared to its neighbors so that the optimal 3D, in this case 2D, layout can be found. And this is a relatively fast option and will be faster if you have GPU acceleration, which is enabled in this version of Huygens, as you can see in the top left in the main window. And with that, it is almost done with finding the optimal layout. As you can see, there are small minor adjustments, but the data set was already pretty nice from the preview, as we could see. At this point, you can choose to load a microscopic parameter file and a deconvolution template, which would allow you to deconvolve each tile before stitching it in the final result. For this data set, I just select to stitch them as they are, and that can be done by clicking Stitch Tiles. And while this is loading, I would like to show you some other images that I have. This will be done in a few minutes. So here I have another session of Huygens running, where we have a pollen data set, which was also recorded from a STEDYCON machine. And if we open that in the 3D visualization tool, if we are choosing, let's say, the MIP renderer, we can really see the detail. This data set was stitched from a 3x3 3D stack image, and these tiles are then stitched together and corrected and even deconvolved. And if we zoom in, we can see the gorgeous detail that is available from this image. And if we want to maybe change the color mode, we can do that from the right hand side by clicking instead of the emission colors, maybe to the global color scale. This will choose an RGB color scheme where each channel is then highlighted in its own color. This is great for looking at the differences between the channels, or maybe we would like to see false color scheme to see where the highest intensities in our images are, or maybe a depth coding, which would show you how deep the object is along the direction of your camera. And you can use this to make beautiful images for your presentations or even for your publications. And it's also possible to make movies with this tool by selecting first frame and a last frame and then exporting that as an MP4 or a .avi file, which you can then also use in your presentations. Let's see how the stitching result is. It's already done. So from here, if we just simply click Done, it will be exported to the main window of this Huygens session. And from here, you can choose to analyze it with the co-localization analysis tools. This will give you coefficient-based co-localization analysis between different channels of your image. Or if you were interested in counting the nuclei inside of this image, you could open them in the object analyzer. And then by selecting, in this case, the fourth channel, we can slide the segmentation slider over here, and this would give you the volumes and the count of how many nuclei there are in your scene. And you can also do distance measurements with this and a lot of other stuff from the experiment preset button over here. So that is all possible from the Huygens tool. And if we then go back to this final image, here we have a nuclear pore complex in yellow and some peroxisomes in red. And this image was also imaged with a STEDYCON, abberior STEDYCON microscope, and this contains 2 STED channels, imaged at 20 nanometer. It's also a 3D image with 150 nanometer Z steps, and because all of the microscopic template files are read from the file, we can use it directly in our deconvolution express tool to get a deconvolved image in a matter of seconds. This also uses the GPU, and as you can see, there's our result, and if we click done, it will be exported to the main window, and we can compare them side by side, and we can visually confirm that the background is reduced a lot and the contrast is improved, and this will be of great use when further analyzing your images, because the noise does not impact your results anymore. So with that, I would like to send you all back to abberior. I believe Janina has some final words. So if there are any questions, please don't hesitate to ask them at the end. I will be there as well, and yeah, back to you.
Thanks a lot, Michel, for the great introduction into Huygens. Now I'll give back to Joachim. He will be our chair for the question session.
Yes, thank you, Michel and Janina, for the presentations. I really enjoyed those. And maybe before we move on to the questions, I want to mention that if you're interested in STEDYCON and Huygens, get in touch with us. We will also give remote demonstrations. You can also send samples to us to have them imaged on the STEDYCON. And if there was no pandemic at the moment, we would also happily bring the systems to your labs for some time for on-site demonstrations. So maybe keep that in mind. Okay, so we have a lot of questions, and so we start with this one. This is a question for Janina. The question is, how accurately does the microscope find a predefined position of the overview scan if the stage has to move? I assume the example you showed were 3 rows within the same larger scanning area.
Yeah, thanks for the question. Actually, in the presentation, the slide I showed, that there were 3 cells in different regions of interest, so the stage had to move in between. And for the Olympus stage, I have here the precision is much better than 500 nanometer, and I think in this specific example, it was even below 100 nanometers. So the stage works quite reliable, but of course it depends a bit on the stage model.
Okay, thank you, Janina. Here is a question for Michel. How can I best inspect my data after deconvolution, and can I still quantify my signals after deconvolution?
So yeah, thanks for the question. So in Huygens, we offer various visualization tools. One of them is the twin slicer, and you can use that to compare 2 images side by side. For instance, you can have on one side your raw non-deconvolved image, and on the other side your deconvolved image, and you can do line intensities along these images, and our results are reliable because we conserve the intensity and the PSF of the images before and after deconvolution, so that the analysis that you do on your deconvolved image is fully reliable. And afterward, if you have any more questions about this, we have you can download the technical notes on our website. And also we have a webinar on true deconvolution, which was a while ago. And there's a lot of information available on our website.
Okay, thank you. Another question for Janina. Is the multi-positioning only available for systems boards starting from now?
No, definitely not. So we can upgrade every system that's already in the field. Of course, you need to have a motorized stage on your microscope, but if you don't have it yet, we can also provide one.
Okay, good. Another one for Michel. The auto-vignetting correction, as shown in the presentation, seems to work nicely. What are the limitations, and how will this work best?
Yeah, so first of all, if your stitched image does not suffer from vignetting, then you don't need to do the vignetting correction. However, if you do notice it, then it would be best if you use the automatic vignetting correction if there's a lot of data available in each tile. So a good overlap between the tiles and sufficient structure in the tiles is then necessary for the automatic vignetting correction to work. And if that is not the case, then you can image a dark field and a flat field image, as I said, and a flat field image can be acquired by using a uniformly labeled slide, which then can be entered into the Huygens stitcher at the stage of the vignetting correction to correct for the vignetting with your specific microscope in mind.
Okay, and we have two short questions for Janina. How many active ROIs can be chosen for one run? Do you know that?
Yeah, this will be around 100 regions of interest at the moment.
Okay. And another short one, can you restore settings from a previous image acquisition?
Yes, that's actually quite easy. So here we have two options. Either when we define the session, we can just load an old image and then the settings will be directly taken over. Or alternatively, we go into the image gallery and choose the image there that we like best and which settings we want to recover, and just click inside the image gallery onto recover settings, and then the settings will be sent over to the imaging software. And from there you can start directly imaging with the same settings.
Okay, great. So I think we have very many questions left, so thanks for the large amount of questions, but I think we will answer the remaining questions by email. And if you have further questions that you did not pose so far, also feel free to contact Janina and Michelle directly, as seen on the left-hand side, or any of the other contact addresses. Yeah, thanks for joining, and I hope we can soon meet in person again, and stay healthy and goodbye.
Yes.
Bye-bye.
Bye.